A modern microchip and a 19th century light bulb are connected by a lineage that isn't immediately obvious to us. While one powers laptops and the other provides light, the core logic of the digital age was actually refined inside these glass vacuum chambers. In the early 1900s, communication networks were struggling to scale. Electrical signals sent over telegraph lines or telephone wires naturally dissipate over distance. To keep a message moving from one city to the next, those fading signals had to be boosted. This was the job of the mechanical relay. When faint current enters the device, it powers an electromagnet that pulls a metal switch closed. This movement completes a path for a fresh battery, boosting a secondary circuit to continue the journey. Relays were efficient enough to handle the simple on-off pulses of Morse code. But because they relied on a strictly physical binary output, a metal arm that was either touching or not, they couldn't move fast enough or delicately enough to amplify the complex, fluctuating waves of a human voice. In 1937, Claude Shannon realized that George Boole's abstract mathematical logic, where every statement is either true or false, perfectly matched the physical reality of an electrical switch. A 1 was simply a closed circuit. A 0 was an open one. That same year, George Stibitz proved this could work in practice. At his kitchen table, he wired together scrap relays and light bulbs to create a half-adder, a device that used electrical switches to perform binary addition. This is a basic AND gate. In this configuration, a light bulb at the end of the line will only turn on if switch A and switch B are both closed at the same time. When you close both switches simultaneously, the path is complete, current flows, and the carry bulb illuminates. You've successfully forced the hardware to calculate that 1 + 1 = 2. This proved that electricity could do math, but the mechanical relay was a loud, cumbersome bottleneck. These switches were slow, and because they were made of moving metal parts, they were constantly subject to friction and mechanical failure. To build a computer that could handle complex equations at high speeds, engineers needed a way to perform this exact same logic without moving any physical parts at all. The solution began with an observation Thomas Edison made while perfecting the incandescent bulb. He noticed that the inside of his vacuum-sealed glass would eventually turn brown, but curiously, the discoloration only happened on the side of the bulb connected to the positive wire. This is thermionic emission. The filament gets so hot that electrons boil off into a cloud of negative particles. In a vacuum, they accelerate toward the positive wire. Most whiz past and crash into the glass, creating the brown stain Edison noticed. By the early 1900s, scientists like John Ambrose Fleming and Lee De Forest realized they could control this flow by adding extra electrodes into the bulb. This led to the triode. It consists of a heated filament in the center, a solid metal plate on the outside, and a sparse wire mesh, called the grid, positioned right in between them. By applying a tiny amount of voltage to that grid, you can control the massive flow of electrons moving toward the plate. This acted like a sensitive valve, allowing weak telephone signals to be boosted with incredible precision over thousands of kilometers. Beyond audio amplification, the triode offered a second function to early computer scientists. It could operate as an electronic switch. Apply a negative voltage to the grid, and it repels electrons from reaching the plate. The current stops, a 0. But a positive grid pulls electrons through to the plate at maximum capacity. The switch is on, a 1. This process happens at near instantaneous speeds, with no noise and absolutely no moving parts. It solved the problem of mechanical wear, because there is nothing to break. You are simply moving electrons through a vacuum. By removing the mechanical lever entirely, the light bulb became a fast, friction-free digital switch. In 1945, the US military realized this potential at scale with ENIAC. They replaced the slow mechanical relays of earlier calculators with nearly 18,000 vacuum tubes. ENIAC weighed 30 tons and required 175 kilowatts of power, enough to run a small town, but it could perform 500 operations per second. It was the first time a machine could solve complex ballistics or nuclear physics problems in hours instead of weeks. But while ENIAC was a breakthrough, it also highlighted a massive bottleneck. These computers were still running on what were essentially fragile, high-maintenance light bulbs. The filaments required constant heating, which meant the computer used massive amounts of power even when it wasn't calculating anything. And because those filaments would eventually burn out, the machine rarely ran for more than a few days before a tube had to be found and replaced. Because they relied on a physical vacuum and heated metal, these machines were at their limit. They could never be shrunk down to a size that was practical for a desk, let alone a pocket. The digital age only truly matured when engineers found a way to replicate this exact same control over electrons without the glass bulb, moving the entire process out of a vacuum and into a microscopic, solid piece of silicon.